Okay, good morning friends. In last lecture we discussed about the lens maker's equation, that means the reflection by a convex lens. Here, what are the equation we obtain? 1 upon f is equal to n to 1 minus 1 into bracket 1 upon I1 minus 1 upon I1. This equation is known as the lens maker's equation, and also we obtain the equation of a lens. That means the relation between the object distance, image distance, and focal length of a lens. Okay. Now, on the base of this, we are going to discuss about the illustration. Illustration 9.7 is given. Is that a magician doing a show use a glass of a lens of the factor index 1.47. This glass is disappear when it dropped in a liquid. That means a magician during his show makes a glass lens with factor index 1.47 disappear in a drop of a liquid. So find the factor index of a liquid. So frequently and also in this type of the show we saw that the magician has the one glass when it immersed in a liquid, so glass is not shown. What is the reason? Here the reason is the physics reason. If the material of the glass and also whatever the material in which this glass is immersed, both effective index are same, at that time the glass is not shown. Like today, in a glass, suppose the water is filled. As we insert the many drop of water, so this water are not shown separately, are mixed up. So here the same thing takes place. Here the glass is also mixed up with a liquid. For that purpose, now the effective index of a material of the glass is equal to 1.7 and effective index of the liquid we have to find out. And also we have to give the answer after last is that this liquid is a water, yes or no. Now for that purpose, if the material of a glass and liquid has same effective index in such condition the glass is disappear in a liquid. Therefore, we are using this equation 1 upon f is equal to n2 minus n1 upon n1. Here 1 upon I1 minus 1 upon I1. Okay. Here n2 is equal to n1. Therefore 1 upon f is equal to 0. Therefore f is equal to 1 upon 0 is equal to infinite. That means the focal length of the glass in this material becomes infinite. Therefore, the glass is not shown in the liquid. Thus, the effective index of a liquid is same as glass. Same as a glass. That means N1 is also 1.47. And liquid is not a water. Liquid is not a water because the liquid has the effective index is 1.47, while the water has the effective index is 1.33. Therefore, given liquid is not a water, there is a only I think approximate the glycerin, because for a glass there is a 1.5 while the glycerin has the effective index is 1.47. Now the next illustration is 9.8. Here, now next illustration is 9.3. It is most important because there is also probability to ask in forward question, because we have to complete this numerical in 3 steps. First is the lens with the focal length is 0.5 meter. Find the power of the lens. Now, first thing, what is the power? Power is the capacity of a lens to diverge or converge the incident light. Or the diverging or converging capacity of a lens, that is known as the power. That is known as the power. What is the diverging and what is the converging capacity? We know that in a convex lens, there's the light are incident on it. So this light are focused at any point on the principal axis. So there is the converge. That means the convex lens converges the incident light. While the concave lens, whatever the light is incident on a concave lens, after the reflection they are diverged from focus. So there is the divergence. Okay, we discussed in detail about the power in next topic. So, in short, the power is the reciprocal of the focal length. Power is the reciprocal of the focal length. P is equal to 1 upon F, and the unit of the power is diopter or meter inverse. Therefore, first we need to find out the power. So, power of a lens here, focal length is positive. Therefore, given lens is convex lens. Here, F is positive. So that it is convex lens. Because in the sign convention we discussed about that. For the convex lens, the focal length is positive. For concave, the focal length is negative. Therefore, power P is equal to 1 upon F is equal to 1 upon 0.5. 1 upon 0.5. Therefore, how much power? 0.5, that means the 1 upon 5 by 10. Therefore, 10 by 5, that means the 2 diopter or 2 meter inverse. 2 meter inverse. That is 0.5 bars, half bars. After that, now in second part, a double convex lens has the two radii of curvature 10 cm and 15 cm are used in a medium. What is the effective index of this convex lens? For that purpose here, the 10 cm and 15 cm, we have to find out the effective index of this material. Okay. Now, actually the convex lens is this way. So as you consider this, when we discuss about the lens and depth, we also discuss this thing. So there is the for second surface center of curvature, and for there is the first surface, the center of curvature C1 here. So there is our I1 and there is our I2. So according to the sign convention, here we consider the I1 is positive. This point is optical center O. So there is the I1. So in this direction, there is the direction of incident A. I1 is positive, I2 is negative. Therefore, we consider I1 is equal to 10 centimeter, I2 is equal to minus 15 centimeter. Find out the A. Okay. For that purpose, here we are using the lens maker's equation. Second part, the lens maker's equation. 1 upon F is equal to into minus N1 upon N1 into 1 upon I1 minus 1 upon I1. Here N2 is equal to N. Effective index of material of a lens, and N1 is equal to 1. That is the refractive index of A medium. Because outside is A medium both sides. Therefore, our equation becomes the 1 upon F is equal to here n minus 1 upon 1, and here 1 by 10 minus 1 by 50, minus 1 by 50. So here first simplified. What's upon here? That is the n minus 1. Here 150. Here we can add the n minus 1 upon 1. Here 1 plus 1 by 10 plus 1 by 15. Therefore LCM is 150. 15 plus 10. So it's equal to n minus 1 upon f. So here 25. So here 150. So 1 by 6. So n minus 1 into 1 by 6. Clear? Okay. Therefore, we have to calculate the n. Now, focal length of a convex lens in A medium is given f is equal to 12 centimeter. Therefore, 1 by 12 is equal to n minus 1 into 1 by 6. So here there is a cancel out. 1 by 2 is equal to n minus 1. Therefore, n is equal to 1 plus 1 by 2. That means 3 by 2. Therefore, n is equal to 1.5. That means the lens is made from the glass material. So there is the refractive index of the material of a glass. This convex lens is used in the A medium. Clear this? Only we are using the lens maker's equation to calculate the refractive index of material of a lens. Clear this thing? So first we calculate the power, and then using the lens maker's equation here, n2, n1 are given, I1, I2, I1 given. We have to calculate the n2. n1 is the refractive index of material of A medium. Focal length is given is 12 centimeter. Okay. So thus we find out the refractive index of material of A lens. Now in third part here in A medium, the focal length of the lens is given to 20 centimeter. When this same lens is used in water medium, so what is the focal length? Here the refractive index of water and glass medium are given 1.33 of water, and for glass is 1.5 is given. Okay, now we calculate it. Now, third part of this illustration. Here, the focal length of a convex lens in A medium is given. There is the 20 centimeter Fa. There is the 20 centimeter in A. This lens now used in a liquid or in a water medium. We have to find out the focal length in liquid, in water. The refractive indices for A, that is given as the n is equal to 1. Now, for lens, Ng is equal to 1.5, and for water, there is the Nw is equal to 1.33. Now, this information is given. In this case, here the radius of the curvature for double convex lens is not given. While in the second part, here the refractive index of material of a lens is not given. but the radius of the curvatures are given. So second and third parts are quite different. So first we are using in A medium. From Lenz-Makers equation. Lenz-Makers equation is 1 upon f is equal to n2 minus n1 upon n1. We have 1 upon r1 minus 1 upon r2. Here n2 is our effective index of the glass medium, and n1 is our Na, the effective index of our A medium, and F is equal to Fa. Therefore, 1 upon Fa is equal to Ng minus Na upon Na. Now here, 1 upon R1 minus 1 upon R2, there is the equation. Now, in water medium or the liquid. Now in water, so there is the 1 upon Fw is equal to Ng minus Nw upon Nw. Here 1 upon R1 minus 1 upon R2. That means the Lenz-Makers equation we can write for. So the same length is used in water medium. At the time, instead of the Fa, that means the focal length in air, now the focal length in water medium. Effective index of material of a lens is Ng is N2, and which medium in which we are using the lens, that is our N1, the water medium, therefore Nw. We require the Fw, therefore taking ratio of equation 1 to 2. Therefore, 1 upon Fa, 1 upon Fw is equal to Ng minus Na upon Na. Now, reciprocally multiply this in W upon Ng minus Nw. So left hand side, Fw upon Fa is equal to Ng minus Na upon Ng minus Nw into Nw upon Na. Nw upon N. We require the Fw. Fa is given, there is the 20 centimeter. Ng 1.5 minus 1, here 1.5 minus 1.33, here Nw 1.33 upon 1. By substituting the value and simplifying this, we obtain the Fw is equal to 78.2 centimeter. There is the focal length of a lens in water medium. So Fw is equal to 78.2 centimeter. Now, on the base of this, sometimes the one bias question is asked like that way. In A medium, the focal length of a convex lens is given. Now, this lens is immersed in the liquid. This lens is immersed in the liquid. So its focal length is increase, decrease, or remain constant. So this type of question is asked because here from this equation or this numerical we say that in A medium the focal length is 20 centimeter, but in water medium the focal length is 78.2 centimeter. Therefore there is the increase, right? Therefore in liquid the focal length of the lens is increased in the A medium. Clear this? Now the next numerical from exercise 9.5. A small bulb is kept at bottom of a tank containing a water up to the 80 centimeter. Containing the water up to the 80 centimeter. So S is equal to 80 centimeter is equal to 0.8 meter. Find the area on the surface of a water from which the light is immersed out. Immersed out. The effect index of liquid is 1.33. Is 1.33. So what this numerical says that here the one tank, a small bulb is placed at the bottom. There is the A, or a small bulb. There is an object O. Now here the water is filled in this tank up to the height H. H is equal to 20 centimeter. 80 centimeter. There is the H. H is equal to 0.8 meter. There is the bulb. So we know that according to the total internal reflection, the rays from the bulb coming out from this water, if the ray coming from the bulb makes the angle of incidence is either equal to critical angle or less than critical angle. If the angle of incidence is more than critical angle, so what's happened? According to the total internal reflection, this light not coming out from the water. For that purpose, here we consider the two rays. This makes the angle of incidence IC. Or there is the perpendicular. So this angle is also the critical angle IC. At the time, these rays are reflected on the surface separating the two medium. Up to this condition only, the light is coming out from this area. There is ODS, so there is a radius of point A and there is the point B. So ODS is the radius of this area through which the light is coming out from the surface of the water. Again, our question is that a small bulb is placed at the bottom of a tank containing a water up to the 80 centimeter height. What is the area through which the light is coming out from the surface? The effective index of the water is given 1.33. Here is according to a total theory, total internal reflection from total internal reflection. If I is greater than IC, the light is reflected in the same medium. That means not coming out from the liquid. So from figure, consider right angle triangle O dash OA, for the O dash A. Now tan IC opposite to the adjacent opposite is O dash A upon O dash O upon O dash is equal to R O dash. Therefore, radius R is equal to H tan IC, equation 1. And sine IC, sine is opposite upon, like this way, And also we know that the sine IC is equal to 1 upon n. Therefore, sine IC is equal to 1 upon 1.33. So it's equal to 3 by 4. For sine IC, yes we do the right angle triangle. So this angle is IC. Sine is opposite to the diagonal. Therefore, there is 3, there is 4. And adjacent is root 7. Root 7. So that is the equation number 2. And cos IC is equal to, cos is equal to adjacent upon diagonal, root 7 by 4. Therefore, tan IC is equal to sin IC upon cos IC. Therefore, sin IC 3 by 4 upon root 7 by 4. That is the 3 upon root 7. 3 upon root 7. Now, we require the area through which the light is coming out. So, area is equal to pi r square of this area. The area through which light coming out is equal to pi r square. So pi r is equal to, from equation 1. So there is the a square tan square IC. Pi is equal to 3.14, h square 0.8 square, tan IC is this. Therefore, 3 upon root 7 whole square. Therefore, we obtain that is the 2.58 area is equal to. So, approximate 2.6 meters square area through which the light is immersed out from the. So, where is the numerical? The concept must be clear about the total internal reflection. If the incident light makes an angle within critical angle at the table second, this ray of the light is reflected in the same medium. Otherwise, they penetrate the medium, that means enter the other medium and we obtain the light. For that purpose, first we find out the tan IC. Tan IC is equal to R upon H. For this area, I is required. Okay. Therefore, I is equal to H tan IC. Now, the value of tan IC is required. For that purpose, we take the sine in both sides. And at last, we substitute the value of R is equal to H tan IC in area. So, we obtain the A is equal to 2.6 meters. Clear? Okay.